In this video, we're going to look at the different forms that elements can take. Elements can exist in their atomic form as individual atoms, they can exist as molecules, or they can exist as networks. You might be surprised to hear that very few elements on the periodic table exist in their atomic form. Group 8, known as the noble gases, are the only 7 elements that exist as individual atoms. Take, for example, a typical party balloon. These are filled with helium gas, and that helium gas is made up of individual helium atoms. Another noble gas, neon, you find in a lot of those neon signs that are at local bars and restaurants. The rest of the noble gases will exist in varying concentrations in the world around us. That is, with the exception of oganesson. Oganesson is a recent addition to the periodic table back in 2015, and the chemistry hasn't really been investigated yet. But we do know that it is an unstable radioactive element that is predicted to have noble gas behavior. Other elements in their pure form exist either as molecules or networks. So what this means is that for an element like hydrogen is that we won't find individual hydrogen atoms floating around in the air around us. We would find hydrogen molecules. And hydrogen is one of the diatomic elements. There are 7 diatomic elements, and these are 2 atoms held together by a chemical bond. So looking at hydrogen, the simplest form of hydrogen is H2. And we can write it like this, where the line indicates the chemical bond where electrons are shared. And we'll talk plenty more about chemical bonding in later lessons. But for now, we just want you to recognize that there are diatomic elements, and 7 of those you need to know. We can write this more simply as H2. So elemental hydrogen is H2. The other diatomic elements form the shape of a 7 on the periodic table. We have nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. So those 6 plus hydrogen make our 7 diatomic elements. The other way that we will find elements is in networks. And this is where individual atoms will bond to other identical atoms, forming these extended structures. And this can come in a variety of ways. For example, carbon can exist as graphite, diamond, or a fullerene. And these are 3 distinct types of carbon known as allotropes, meaning that they have the same composition. They are all carbon, but they are different forms of carbon. So graphite, we can look at the structure and start to see that there are sheets of carbon networks layered together. Contrasting that with diamond, we see that there are significantly more linkages between the carbon atoms in diamond. And when we think about the properties of graphite versus diamond, we can see how the structure at the molecular level could influence these properties. Diamond, known for its strength, has significantly more bonds than graphite, which is pretty soft and malleable, used in our pencils that we use to write with. And the last type of carbon allotrope is the fullerene, which is a C60 buckyball shape, where we have 60 carbon atoms arranged in a spherical structure. Carbon is not the only element that exists in a number of different allotropes. Oxygen is another example. Take O2, the diatomic form of oxygen. This is the most stable and most common form of elemental oxygen that we'll find in the atmosphere. But ozone, which we've probably heard about before, is O3, is another form of elemental oxygen. It consists of only oxygen atoms, making it an allotrope. Ozone is responsible for the name of the ozone layer, and it does play a role in protecting us from the sun's rays. It's more common to find elements existing in compounds, and a compound is formed when elements of one type combine with elements of a different type. And there are 2 different kinds of compounds. There are molecular compounds and there are ionic compounds. We're going to focus right now on molecular compounds, and we'll discuss ionic compounds in a video that comes later on ions. Molecular compounds consist of different elements held together by a chemical bond. And yes, that phrase chemical bond is coming up again, but I promise that we will talk about what a chemical bond is in later lessons. For now, let's look at some examples of molecular compounds. Methane, CH4, is an example of a compound that is molecular, consists of two elements that are held together by one or more chemical bonds. Water is another example that I'm sure you're familiar with, and ammonia, commonly used in cleaners. These three molecules, we can see their structures, and we represent them using the molecular formula. And the molecular formula tells me the number of atoms present and the type of those atoms. So the type is indicated by using the elemental symbol, and the number of atoms of that type is indicated by the subscripts indicated in the chemical formula. So we have 1 carbon and 4 hydrogens in methane, 2 hydrogens and 1 oxygen in water, 1 nitrogen and 3 hydrogens in ammonia. Throughout this course, we'll be representing molecules in a number of different ways. And to look at just a few of the ways that molecules can be represented, let's take an example. Let's look at ribose. Ribose is the sugar that makes up the backbone of RNA. Ribose contains 5 carbons, 10 hydrogens, and 5 oxygens. And one way to represent the structure of ribose is with the structural formula. And as the name implies, it gives us structural information, such as the connectivity of atoms. We can see that carbon is bonded to carbon in this position. This carbon is bound to a hydrogen and an oxygen directly as well. So in addition to the connectivity, we get a little bit of three-dimensional information. This wedge is a way of representing a bond that is coming out of the plane of the board, screen, whatever you're looking at. So that is coming out towards you. The dashed bond, on the other hand, is going away from you or into the screen. Another type of representation is the ball and stick model. The ball and stick model still gives us that structural information of atom connectivity, but it also gives us more information about the bond angles and three-dimensional structure. So we have more accurate bond lengths and angles in the ball and stick model. A space-fill model is the third type of representation that we'll see. And here, the space-fill model takes into account the atomic radius of each atom in the molecule. So you can see exactly how much space each of those atoms takes up in our structure. And you can see that while the structural formula looked like there was a big empty space in the center of the ring, here in the space-fill model, you can see there's really not a whole lot of empty space available due to the radius of those atoms being so large. And the final way that we'll represent molecules will be with what's called a skeletal formula when we get to the organic chemistry portion of the course. In the skeletal formula, it's very simplified. We omit atoms like hydrogen, and they're implied based on the rules of valence that we'll discuss later in the course. So we don't see hydrogens explicitly as they are attached to carbon atoms, and each carbon atom represents a vertice of my chain or ring. So please let me know if you have any questions, and thank you for watching.